节课呢是关于医疗器材开发工具 MDDT 的介绍。那在 ITIS 跟 ZMT 的共同努力下，第一款用来评估主动植入式医疗器材的运算型医疗器材开发工具呢，在2019年的12月获得了美国 FDA 的核准。那我们这一次的课程就是邀请到瑞士 ITIS 的专家 Dr. Goran 跟 Dr. Crano 博士来共同分享这款工具的运作原理。Now, welcome Dr. Goran and Dr. Crano. Thank you.
Thank you very much. Hello, everyone. I can't really see any of you, but hope you can see me well. So I'm here to talk about the tool that we've developed at the ETIS Foundation, which is called IM Analytics with MRI-XVIP 1.5T/3.0T and PC-lib. It's the best name we could come up with, and how the FDA has qualified this tool for assessing MRI implant compatibility. So let me introduce myself. My name is Tolga Goran. I'm working at the ETIS Foundation in Switzerland. We're a nonprofit research foundation, spin-off of the ETH Zurich. And we also have two commercial spin-offs, so Schmidt and Partner Engineering and ZMT Zurich MedTech. ZMT Zurich MedTech is focused on problems associated with MRI implant safety, and we provide validation hardware for this application, as well as the simulation platform SimForLife. And the ETIS Foundation, where I work, is developed, among other things, the virtual population anatomical models that I'll be showing, is focused on research, standardization. And so I'm working on customized research there, which includes a lot of implant safety projects, particularly RF compatibility and gradient compatibility. And I'm a member of IEC 60601-233, which is the MRI system standard, and ISO 10974 Joint Working Group, which is the MRI active implant compatibility standard. And so the ETIS Foundation works in terms of research and in terms of customized research with many partners around the world. Let me make this a little smaller. So including all the major telecom companies as Schmidt and Partner Engineering, almost all the major implant manufacturers, so Boston Scientific, Abbott, Biotronic, Sorin, Livanova, many cochlear devices, spinal cord stimulators, and more. We work with all the MRI system manufacturers, so Siemens, GE, Philips, and Hitachi, all the major ones, as well as other manufacturers. And we work closely with regulators around the world, including FCC, FDA, and European and Asian ones as well. And we participate in many standards focusing on wireless telecommunications, safety and standardization, as well as the ones I've mentioned. So we performed a number of customized research projects that led to successful regulatory submissions, which helped us to develop the tool that I'm now going to be telling you about. We publish pretty strongly in journals and conferences, and our group citation index has been going up pretty continuously since we started in the late 90s. So this is the tool that I'm going to be talking about. This is a screenshot of the qualification report, which is available on the FDA website. So this document includes some kind of summary of what I'm going to be giving the background on. So if you're of any doubt, you can always just look at that. This is the version 2 revision of the standard of the tool, which has included some updates that I will explain. Mainly improvements. So version 1 of the tool is still qualified, and version 2 just has some extra features that have been added. So this document describes the latest version. So I'm going to give a brief introduction to the ISO 10974 Tier 3 workflow. I wonder if there's a way, there we go. I can make this WebEx thing smaller. The ISO 10974 workflow for assessing the compatibility of implants with RF fields in MRI. So the first step is to develop a model of how your device, your AIMD active implanted medical device, responds to EM fields, so RF fields at 64 megahertz or at 128 megahertz. And then this model has to be validated. And so you can predict with this model how your device will interact with any incident field applied to it. In parallel to this, you have to determine what the fields are going to be that apply to it when the patient is inside the commercial scanner. So this involves, without the implant, understanding what kind of fields are going to be present inside the human body during the MRI. And then you combine the incident fields, which happen during the MRI, with the response of the device to those fields to get the local response, which can be either a voltage response, induced voltage inside the IPG, or heating at the tip if power goes out to the tip and into the surrounding tissue, from which you can do a risk assessment. Oops, I meant to click that. So these components, the development and validation of a model of the item, are typically done by a test lab, and then this piece, which is takes this as an input and then has this independent step, is what the FDA qualified medical device development tool can do, which is what I'm going to be talking about. And then the outputs of this can be converted into a risk assessment or injected or radiated test for voltages by a test lab. So this is how a model of the device is created. I go through this very quickly just to give you the background on what these inputs would be. So we take a device and we apply piecewise fields along the length of the device at 64 megahertz, and we measure the response either of the tip, which is in contact with the tissue, the E fields around the tip, or with the voltage in the can. So the voltage is induced at the other end of the lead in the device, and we measure the magnitude and phase of these responses as a function of the pulse that's swept along the tip, and this creates a so-called transfer function measurement. For a passive implant, instead of a transfer function measurement, because it's not a long device, we would have a more simple, like, amplification factor. So if you put in a field applied to it, how much does it amplify those fields? And then this can be validated with radiated tests. This is shown an RF benchtop testing system where you would put the implant in some orientation, apply some fields, and see if the predictions of your model in terms of how the implant responds to those fields match the measurements that you actually create. So you would say, apply this tangential E field, apply that tangential E field, and see if your predictions from your model match what you actually measure under those circumstances. And then you end up with this validated model. So this is in 3 sentences what the test lab has to do, which is a whole other topic that one can cover. Now, to the tool. So I can start by introducing the virtual population, which started as the Virtual Family version 1 project together with the FDA and some universities and the ETIS Foundation. It was released originally and it was developed in the 2004-2007 timeframe, started with 4 anatomical models, and then more and more were added with time, and they were converted into the virtual population version 3, and now there's some virtual population models that have updated to version 4. These have included over time higher resolution tissues, better separation and identification of tissue properties, including a tissue properties database that the ETIS Foundation maintains, and ability to do things like pose and morph the models, as well as now improved performance on things like neurostimulation and blood vessel resolution. So these are the anatomical models. I hope the video is playing with a reasonable frame rate. So each of them has, the version 3 models have more than 300 individual tissues, and they cover a wide range of, there's a lot more than this, by the way, this is an older video. They cover a different range of sizes as well as BMI. So these are the models that are used in the MRI-XVIP data set, which is part of this medical device development tool. So there are more than this, but these are the ones that we use for MRI in version 2.0 or 2.1 of this tool. So you see the body mass index and the age. These curves represent some population averages, and then the points are the names of these anatomical models that we have, which are named after jazz musicians. We have the newest ones are in version 2 that were added. Were a Korean model called Yunsun that was developed from a cadaver in partnership with with 2 Korean universities, anatomical groups, as well as some morphed models of previous, morphed versions of previous models. So Ella 26, Ella 30 with a BMI of 26 and 30, and FATS with a lower BMI. We've also got a male Korean model that will be introduced very soon, as well as another Western model in the next version that's coming up later this year. So this is the anatomical model Yunsun, the newest one, Korean female. you can see that due to the improved sectioning and tools since the original models came out, she has a fully realized peripheral nervous system. So all the nerves are mapped, and also their tissue properties are assigned. And this doesn't show it, I think, but she also has a full vasculature, peripheral vasculature, with all the blood vessels connected. And on the physics-based morphing side, we have the ability now to make Duke Ella fats more muscular or more fat in a realistic way. One model that we're working on right now is an extremely obese, we call him sumo fats. So it's the fat model with a lot more fat to represent extremely obese, like a sumo wrestler kind of person, which would be tested with very large MRI systems. So here's the skinnier fats, and the fatter Ella and the Korean model Yunsun formed MRI-XVIP version 2. So MRI-XVIP is actually what happens when we take this data set of patient models and we apply a range of bird cages to them, so RF coils from the MRI, and in a variety of positions to create a large data set of the fields that can be experienced by these characters during MRI scans. So here's a video showing that a little bit. So we have 10 birdcage models, which represent the span of all commercial MRI coils available today. So closed bore 1.5T, 3T coils. And then we apply every possible coil to every possible scanning position and every possible polarization for all 12 anatomical models. And we end up with a data set which is 50 to 70 terabytes, depending on how you count it, of E-fields data. So induced E-fields during MRI scans. So how the E-fields are in the head, in the neck, in the bicep, all of this is captured in the 70 terabyte data set, which covers all fields that can be experienced by these anatomical models during any MRI scan in a closed bore scanner. We have shown in, this is some results that we're going to show in the upcoming ISMRM, that the most important thing about predicting patient deposited power for an active implant, so how much power will be picked up by an implant and deposited in the tissue, is the patient anatomy. And patient anatomy doesn't directly correlate with something like BMI. So it's not always the case that the fattest patient has the highest fields, because the scanner knows how fat your patient is and will actually put in less power potentially. It also depends on your scan position. It depends on your implant. But what we've shown in this work is that using these 12 anatomical models and only a single generic device, we can show that each device can be, each patient can be the worst case for at least one configuration. So here you see the deposited power for 12 anatomical models. And for each anatomical model, there's a point where it's the worst case, including the skinny boy, including the Korean lady, including the fat guy, including everybody. So everybody's the worst case for at least one scan in at least one position. And this is without considering different devices. It's all with one device, 2 polarizations, and this is at 128 megahertz in this example. So the takeaway from this is that in order to define your safety envelope of what you can experience during an MRI, you need the widest possible range of anatomical phantoms. And that's why we keep expanding those. And then the other part of the tool is the IM Analytics. IM Analytics is a numerical solver. Basically, once you have a field inside the body along the lead that your device is on, and you have a model of your implant, which is how the device will respond to that lead, basically you just take those 2 curves and add them together or multiply them and integrate it, and you're done. It's actually something you can do in Excel or by hand. But what you have to do is generate this for a whole range of data sets. So you need to, 12 anatomical models, 10 bird cages, head to foot scans, different polarizations, and you've got maybe more than one implant model. And you also have to consider the scaling of that. So are you running your MRI at normal mode? Are you running it at first level controlled mode? Are you running it at B1 plus limitation instead of a SAR limit? Basically, this ends up being an enormous amount of data. And then this is a verified numerical tool, which just does all that math and gives you the statistics. So what it tells you is, okay, if you set your MRI to normal mode, what does normal mode mean for fats when he's being scanned with a 70 centimeter coil in his neck? What does it mean for Billy when she's being scanned with a 75 centimeter coil at 30 centimeters down, whatever. So it figures out what normal mode is for every position. and then it does all these computations, extracts all these fields, and creates a set of predictions which have a range, a statistical range from low to high. So over all 10 bird cages, over all the anatomical models, here's the range of values you can have for a scan in this abdominal position, let's say, for Duke. Maybe this is Duke. And then you can take the maximum, the 95th percent, or the median result. Typically, people use either the maximum or the 95th percent because there's usually a few cases that are much worse than the others, and those change the statistics. And so once you've done this for all 12 models and for all your data, you have an envelope and you've covered the maximum or 95th percent range of what that envelope can be for all patients undergoing MRI scans. So this is the tool that's being used. It has a pretty simple GUI. You select your anatomical model. Here's some example routing, so cardio routings or deep brain stimuli routings. You choose your bird cages. You choose your operating mode, so normal mode or first level mode or whatever. You load some polarizations, or you just use circular polarization if you just want to pick that from a drop down, and then you hit run, and it takes about 30 seconds, and then it spits out all the, these are the normalization factors. So this is what normal mode means for these scanners for each coil at each position. And then here are the results. So this is the distribution of deposited power that I've just showed. So you see the maximum value, 95th percentile, and the median, and you can also get this histogram view of all your data, and you can easily export this and so on. Now, there's also more functionality that's available in a notebook. So you can basically set up different scenarios or do more complicated things. You can also get, instead of along a routing, you can get in a region, and you can also compute induced voltages and do a lot of other things, normalizing to B1 plus instead of SAR. Many things can be done with this notebook that has that's Python based and uses this API. So here's a summary picture of the GUI as well as a representative notebook model. So what does this tool give you compared to a normal tier 3 evaluation that one would do before this tool existed? So basically, what you see is, like, from top to bottom, what you have to do in order to figure out what a tier 3 evaluation according to 10974 would give you. So at the top, you have to start with a test item definition. You have to get your test equipment. You have to generate and calibrate your transfer function model, and then you have to verify and validate that transfer function model. So those are the first two slides I showed you. And then to develop the incident fields that you've figured out, so what's going to experience in the commercial scanner, you need to figure out what are the representative coils that cover all the scanners that your patients might be exposed to. So this involves some research because this isn't that easy to find actually, like what kind of coil sizes and so on are there. So very limited data has been published. Patient anatomies, so you'd have to know what your patient anatomies are going to be, scan positions, polarizations, and landmarks. And then you have to figure out if these conditions are customized and if they're worst case. And of course, the anatomies that you're looking at need to be quite detailed because as we've shown, there's a big difference in anatomy based on the results. Then you have to perform a lot of simulations for all of these cases, and then you have to verify and then validate those, and then provide an uncertainty assessment of those. So the MRI XVIP tool lets you just refer to a data set that's been previously derived. You get it in a hard drive, and it's ready to go. So then you have to define your clinically relevant implant trajectories or regions of interest. If it's a passive implant, like a hip implant or something, you draw it in the anatomical models. So either these are the models you're using, or these are the standard virtual population models. And then from those, you need to take from this data all the E fields that are tangential to your trajectories for each exposure condition. So you have to say, okay, what does the scanner limit mean for each of these positions, for each of these whatever? And so in the past, people developed crazy bundles of scripts to do these things, so MATLAB code or whatever. And now this is all done in a verified way with a report by AM Analytics. Then you need to actually just superpose your ETANs with your transfer function model to get your predictions. Again, you need to put in your transfer functions and you need to run it through all this. So now it's all calculated automatically in a verified way. And then you have to verify your tool, but you don't need to verify it if you're using Analytics. And then you have to report the results, including a statistical analysis and a distribution. So this can be done automatically, and you also have to make sure that you're maintaining and continuously improving, as well as providing traceability for all these calculations. So the MRI XVIP library is traceable, and the software is also verified and has version control and so on. And as you've seen, version 1 and version 2 of this tool are both qualified. So I think I'm a little early, but in conclusion, basically we've developed these exposure libraries with the ETIS Foundation, as well as the Sim for Life IM Analytics module with our partner ZMT, which is a tool for evaluating the Tier 3 behavior under multiple exposures, which can be used for Tier 3 or for passive implants as well. And the goal of this tool, which it is qualified to do by the FDA, is to place real measurements of devices in a lot of virtual scenarios, in a lot of anatomical models, that in a range of scans which cover the commercially available bird cages of commercially available scanners, 1.5T and 3T closed bore scanners, and then perform an assessment of the statistical envelope of the deposited powers or induced voltages that can arise from those scenarios. So this was actually the first software tool that was qualified as a MDDT. So until then, this MDD program was quite new a few years ago. And until then, the only tools that had been approved were questionnaires and things like that. So this is the only software tool that's been qualified for use in figuring out if an implant is safe or not. So we'll have heard a little more about ones that are coming out now, but I think we're still the only one that's in this range. And the idea is that you can do an analysis in minutes instead of months. Of course, there's the hope that people that also have their own tool sets that they want to use instead of this can do so. It's not an exclusive qualification, but the idea is that this creates a new standard for what kind of verification work needs to be done and how the results are expected to be traceable and maintained. So that anybody else can compare their results against this, and then they can continue to use their tool if they want. But we believe that this has really set a benchmark in terms of quality for this Tier 3 evaluation, so that people can take this as a solved problem, or even if they present an equivalent solution, and then just move on to other aspects. So my colleague, Dr. Lena Krenold, is going to talk about the other aspects that can arise during MRI implant safety, which include how to figure out the temperature rise, how to deal with more complex implants, and things like that that go beyond what the standard requires or what this workflow can cover. So that's my presentation. Thank you very much. This is us in Zurich at Z43, which is the parent institute of the ETIS Foundation.
Hello, yeah. Okay. Well, thank you, Dr. Gorin. I'll share my screen. Can everybody see my screen? All right, good afternoon. I will be talking or presenting to you some work that goes beyond what Dr. Gorin talked about with the MDDT IM Analytics tool, about estimating the temperature rise, thermal dose, and patient risk assessment from the deposited power that can be derived with this tool. A brief introduction. I'm originally from Germany, but now I work in Switzerland. I obtained a PhD degree in electrical engineering from McGill University in Canada and have a background in RF and medical device development, as well as clinical trials with those devices. Here in Switzerland, I'm a postdoc at the ETIS Foundation, and I mainly work with Dr. Gorin in the MRI implant safety customized research. So I am part of the numerical investigations that are necessary to follow the workflow of the standard and to work with the IM Analytics tool. And I also work in the hardware validation, hardware development that can be used in the test lab, and that's accompanying this tool that Dr. Goran talked about. So first of all, I'll briefly introduce the standard again and the general workflow before I talk about the different tiers in this workflow and explain the power to temperature-rise estimation and work beyond the standard. The clause 8 of the ISO 10974 covers the RF-induced heating of active medical implantable devices, and it's built in a 4-tier approach. Although the new standard that's in, or the new edition that's in review at the moment, will remove the first tier. And it's important to know here that the lower the tier number, the less complex the model needs to be, but at the same time, the more we overestimate the deposited power caused by this implant. And the further we go down the line towards a higher tier number, the less is the overestimation of the deposited power, which opens up the standard or the possible MR scans to a wider range of the population, but it's also compared or connected to more complex models that are necessary. And the IM analytics is mostly used for the tier 3 assessment. So in tier 2, mostly electrically short implants are covered, and this is derived or goes in accordance with the ASTM standard, which is following the testing in an ASTM phantom where the implant is just placed on the side of the phantom and exposed to different fields. And the problem here is that in the ASTM phantom, the electric fields that are induced, if this is placed into an MR scanner, are on average much lower than fields that can happen inside the body. So the tier 2 assessment of these implants include the in vivo estimations, which is included in the MRI XVIP library that we have, where you can define regions of interest, for example, here for a shoulder implant that's short, and you can derive the average E field along the trajectory where the implant would be placed. And then you can, in an ASTM, in a modeling approach similar to the ASTM, you can expose this implant to the fields that can be derived of these in vivo cases, and then you get the deposited power that's caused by this. Here's another summary of this. So usually in ASTM testing, you have an actual MR scanner where you place this large phantom and you place the implant somewhere on the side where the fields are a bit higher, and then you can measure the temperature. But what we do is we actually derive the maximum E field from the previous simulation with all the anatomical models. And then we can expose this in a simulation to the maximum average E field that we extracted from the models. And then we can relate this to temperature rise. And here you see a graph how in red 3T and in black 1.5T, the peak temperature rise that can be caused by an implant is depending on the implant length. And you see that it's kind of a curve that gets to a maximum and then it goes down again. But this is only valid for short implants. If we get longer implants that are elongated, like spinal cord stimulators, for example, we have phase effects that we have to consider, and that's why we would move to tier 3 assessment of these implants, which can cause much higher heating than what you see here. In the tier 3, we would use the IM analytics tool that Dr. Goran described earlier to assess the deposited power in vivo. So we determine the worst case, the worst patient, scan position, coil type with the scan. But this tool needs some inputs that are derived from the test lab and from numerical modeling, which, for example, can be done like this. So we basically need a way to measure the actual implant and the actual implant response, and then to transfer that and scale it to the simulations that were carried out beforehand and that are used in this large library that the IM analytics tool is using. So we would expose, for example, the physical implant in the test lab to an isoelectric field, which strength we know, and we can scan, for example, these are 3 different cases. We can scan in planes above the implant tip the deposited power. So we get a 3 planes of the deposited power distribution that are in 2 dimensions. Then we move to the numerical modeling, which is the part of the ISO 10974 standard as well, and we simulate the deposited power around the implant tip. So we actually get the 3-dimensional distribution of the power, which we can integrate, and we can put a number on this. Now what we try to do is we take these 3 measured planes and we see how they fit into the 3-dimensional distribution of the numerical model up here where we measured. And then we can actually scale the lab response, the in vitro response of the implant to an isoelectric field to the MRI XVIP library, this huge library of different bird cages and incident fields that we can use for the IM analytics tool. And this is how we get a scaling factor from the actual physical implant to this library that we can use to determine the deposited power that this implant is causing. The tier 4 is the most complex part of the ISO 10974 that can be used to determine the deposited power of an active implantable medical device. And this is basically also a tool that we use as a validation for the IM analytics, which contains that we look at the worst case or some of the worst cases of an implant writing, VIP model, a bird cage model, and a scan position. And we actually take the implant, the EM model of the implant, we place it in the VIP in our numerical model, and then we run the full simulation and we extract the power deposition, also the temperature rise, and it should be the same as what IM analytics is giving. Now coming to the essential parts, how do we get actually from the deposited power to the temperature rise and hence the risk assessment, which is what we really care about, right? To estimate if it's safe to put a patient with this implant into an MR scanner or not. This we do also with a set of numerical simulations, because we can't simply place someone in the MR and hope to measure the temperature and that it's safe for him to be used. And the standard, the 10974 standard, actually is mostly talking about the power deposition. But the power deposition itself in the human tissue is not what's essential to determine if it's safe or not. What's important is to know how high is the temperature rise and how long is the temperature rising. Because, for example, if we put our finger over a flame of a candle and do this really shortly, the finger doesn't burn, the skin doesn't burn. But if you put the finger very long there, it burns and it hurts and the tissue is damaged. So this is an essential component, right? So here's an example for a spinal cord stimulator. What we do to assess the power to temperature conversion factor, we look at the actual portion where would the implant be placed in vivo, and we look at the local tissue environment. So the spinal cord stimulator would be near the spinal cord. And here you see 3 different positions that have to be tested, which is all part of the of an uncertainty and sensitivity study that needs to be done if we do simulations to assess how much uncertainty is around what we actually simulate. So here you see 3 different setups. Once the spinal cord stimulator, a simple model, is placed directly at an interface between 2 tissues. Once there's a small offset, and in position 3 there's a larger offset. Now for this, I would construct first and calculate the deposited power that's caused by this, and then I do the thermal simulation assessment of this, which results in this power to temperature conversion factor. And if we look at the different positions and the thermal conversion factor, depending on where it's placed, this factor can be much larger or much lower. So we see in position 2, for example, where there's only a slight offset of the tip between the tissue boundaries, the conversion factor is 506 Kelvin per watt, which is much larger than for some of the other cases that we test. So it's very important that these assessments are done and the power to temperature conversion is done, that we actually define properly what is the actual clinical environment of this implant and what's the uncertainty that's added to this. Because depending on the surgeon who places this implant, it might be closer to the interface or further from the interface, and these are all factors that need to be considered in this modeling. Another portion, which I talked about briefly with the candle example, is the temperature rise. which is necessary to estimate. And what we consider even more important is something that's called thermal dose, or CEM43, cumulative equivalent minutes at 43 degrees Celsius, which is a number that differs for every tissue and determines when the tissue is actually damaged or not. Because some tissues that have a high perfusion, for example, like muscle or skin, means there's lots of blood vessels that can take the heat away from the hotspot and diffuse it or perfuse it. So those tissues, for example, could handle the exposure to a higher temperature longer than tissues that are more sensitive, like a nerve or the brain. And on the left here, you can see a graph that shows over time the peak spatial SAR or the whole body SAR. Doing an MR scan that's 70 minutes long, for example, and the peak temperature increase compared to that. But this needs to be translated into this factor that's called thermal dose, or CEM43, where we hit the point or only after, or already after 20 minutes for some cases, depending on the perfusion model, where there's actually damage caused to the tissue. So these are all factors that need to be considered in the modeling process for the power to temperature conversion. And the images on the left, sorry, my little face is in the way, show that there are different hotspots and that around the body and the neck region, tissue interfaces or organ interfaces that all have different perfusion and power to temperature deposition, and this all plays a role in the thermal modeling process. Do we consider perfusion? That depends on the tissue. Some tissues have lots of perfusion, like muscle and skin. Others have very, very low perfusion. And these are all factors that need to be considered in the thermal modeling of tissues. And it's also a factor that needs to be assessed with regard to the sensitivity of the entire simulation. Now, what can be done beyond the standard? What are some techniques that can be used? Before, in the talk from Dr. Goran, he explained how the principle of the transfer function works, which is usually done in what we call high permittivity medium, which is representing average body tissue properties. But this means that it has a high permittivity and high conductivity. And for some implants, for very specific implants, it leads in the simulation assessment to a much higher overestimation of the power deposition and the heating than it would actually be in vivo, because the most parts of the implant are not in this high conductivity liquid or high permittivity medium. But for example, a cochlear implant that goes inside the cochlea, most part of it is subcutaneous between the bone and the skin and the subcutaneous adipose tissue. So in this case, the new 10974 standard has a tier 4- clause in clause 8, which estimates the transfer function in a heterogeneous clinical tissue model, which can only be derived in simulation, because we can't just put two different liquids in the tank and scan, because they would mix. So what we would do is we measure the implant and the response at either of these tissues. Then we simulate the implant in either of these tissue simulating media as well. And we use this to validate the numerical model that we can derive of the transfer function, which we then use to develop this mixed medium transfer function model that can be used as an input to the IM Analytics medical device development tool. Other things that need to be considered and everybody needs to be aware of that go beyond the implant safety standard 10974 is that increased heating or power deposition can be caused by damaged, broken, or abandoned implants within the human body. If we have multiple leads that are very close together, there can be a proximity enhancement effect. And also the voltage response that cannot only be part of the damaging of the IPG to an extent that it deposits more power or that it damages the implant so that it doesn't work properly anymore. So from my talk, the takeaway messages are that numerical modeling is essential to predict the in vivo power deposition, but with this, we always need to do a sensitivity analysis. So we need to consider how is the implant placed in vivo, what can change, what are the influences of the material and tissue properties that we use. And also beyond 10974, that there needs to be special consideration if an implant lead is damaged or broken or abandoned, and what are proximity effects for patients that have multiple implants that are close to each other, or multiple leads that are close to each other. And then thermal dose and CM43 are important to consider as well. Thank you.
谢谢 Dr. Goren 跟 Dr. Crano 的解说，那就是让各位学员对于 MDDT 这个开发工具有更深一步的了解。那我相信学员可能会有一些疑问，那因为就是连线跟时间的关系，我们会议可能就会结束在这里。那如果大家有问题的话，可以寄信到我们协办单位的信箱，我们会统一收集之后提供给讲者，那请讲者再统一为我们做解答。那顺便再提醒一下线上的学员，就是我们课后会有签退跟测验，那我们开放的时间到6点钟，那请大家务必在时间内就是做好签退跟测验 ，OK， 那